mixtures in it. So what I'm going to do here is just kind of start with I guess when we talk about nutrients, so nutrients, as we know, is plant food, and we need nutrients to grow plants. The challenge with the nutrients is they don't stay in the plant root zone where they need to. That's where they are intended for or needed for. And the issue arises when these nutrients escape plant root zone and end up in water bodies. That's where they become a pollutant. So the key with production system is not only from the economic side, but also looking at the consequences of water quality. We want them to stay in the plant root zone. And there are many areas in the world where we have deficiency of these big three nutrients, nitrogen, phosphorus, and potassium. So we need these to grow plants. And as we go along, I hope that you will appreciate that how we have been grown to be 6 billion in this world, largely because of nutrients. So we can produce more food. So we change the way we used to farm or we used to do agriculture. So before we get into that, so this is my favorite product table to look at it, because I think it kind of gives you a big perspective that we have a lot of elements going around. It's not only the nitrogen and phosphorus. So when we look at, we got nitrogen, phosphorus, which is what we call non-metals, and we have potassium on the other side. So as we know that depending on the location in the product table, these have different chemistries and biogeochemistry. And once we know that, then we can begin to appreciate more that why are they there, what they're doing for, and more importantly, how can we manage them so that they can stay in the root zone. So when we talk about nutrient cycling, it's really the use, the movement, and the recycling of those nutrients in different places. And this all begins with carbon cycle, which is integral to how nutrients recycle, transform into the systems. So when we talk about carbon cycle, it really begins with plants. So plants use carbon dioxide in the process called photosynthesis to grow, and as plants and organic materials decompose, they put carbon dioxide back into the system via respiration. So carbon dioxide goes back into the environment or atmosphere, and in the process of plants growing, they need nutrients. So that's where the nutrient cycling becomes a key to a productive agriculture system. So this is the slide I was talking about. This is my favorite slide to look at it. So as you look on the left side, this is our population going up to 6 billion or 7 billion. And this is a timeline. So when we look here, the nitrogen was discovered in mid-1700, and it took almost 70 years to realize that this is an important nutrient for plant growth. Close to 1900, we discovered what's called biological nitrogen fixation, which means that plants can actually take nitrogen from the atmosphere and meet their partial nitrogen requirements. And then came what's called Haber-Bosch process, and we'll talk about that a little bit. This is when we begin manufacturing fertilizers at industrial scale. So after we begin making these fertilizers, look at this tremendous growth in human population. And partly this has been made possible due to invention of nitrogen fertilizers. And if you look on this side, this tells you how much fertilizers we begin making. So this scale is on teragram. 1 teragram is about 2.5 billion pounds. So currently we make more than 250 billion pounds of fertilizer via a Haber-Bosch process. So again, nitrogen is one of the most fascinating nutrients. And if you are a researcher, it's kind of fun to chase nitrogen because it keeps going in one direction or another direction. So there are many reactions that happen in the soil. Most of them are mediated by soil organisms. And again, it changes from one form to another. Nitrogen is an only element among big three that also has a gas form. So as we know that in the atmosphere, we have 78% of nitrogen as a gas. So it's no surprise that this is how they discovered the Haber-Bosch process, which we'll talk in a minute. So when we look at nitrogen cycle, there are a couple things that you want to notice here. Is this is input. What are we adding into the soils, for example? So I'll start with animal manures, compost, biosolids. We also have legumes who biologically fix nitrogen. We also have plant residues. We also have fertilizers. And when you think about plant uptake, this is where the whole nitrogen cycle comes into play. That the organic residues decompose, they put organic nitrogen back into the soils, then it transforms through these processes, which we will talk in a little bit more detail. So once we have nitrate, which is what plants need in addition to ammonium, then there are a couple things that can happen, the loss mechanisms. So this nitrate can leach. This can also denitrify, which means convert back into nitrogen gas and go back into atmosphere. We can also have issues with runoff and erosion. We could also have issues with volatilization, which we will talk about that in a minute. We also have atmospheric nitrogen, which can fall back and contribute to some of the nitrogen in the terrestrial landscape. This is another way to sort of visualize all those different pools. So these are our main inputs. So we can call them organics, fertilizers, and natural or biological nitrogen fixation. So talking about fixation, since our atmosphere has 78% of the gas, you would think that plants should be able to take it, right? Ideally, you would think that, but it's not possible because nitrogen is one of the most inert gases in the system. It has what's called a triple bond in chemistry. So in order for this nitrogen to be useful, the first thing that plants or industrial process has to do is break this bond somehow. So once the bond is broken, then nitrogen can be combined with other elements to be used by plants. So how does that happen? It happens in the atmosphere. So lightning is very powerful. It can break this bond. So, and this nitrogen can combine with oxygen, and it falls back as nitrate or in the form of nitrous oxides. Another way is that plants are also very powerful. In this case, we're talking about legumes, for example. So legumes can take the nitrogen gas, and there is a particular bacteria that can actually break the bond, and then plants can use it. And then we have another what's called non-symbiotic, which means which means only one person is benefiting. So symbiotic means bacteria benefits and legumes benefit. So this happens mostly in the water bodies where we have algal blooms. There are many species of algae, such as blue-green algae, who can take nitrogen and fix it, and then lead to algal blooms and other issues. So this is an example of soybean nodules. This is where the nitrogen fixation happened. So when we talk about fixation, how much is this in general? So in some crops, such as alfalfa, soybean, you can have quite a bit of nitrogen that could be fixed by these crops. And this is a good thing. What it means is that we don't have to fertilize these to that extent as we have to do with non-legumes and some other examples from other species. So when these crops are grown in a rotation or in a system, you can calculate the legume credits, which means this crop will provide nitrogen for the subsequent crops. Again, a great way to utilize some of the legumes in a cropping system to do that. Now, another mechanism, what is called the industrial process of fertilizer manufacturing, this is Haber-Bosch process, and this is actually an excellent piece in the history that there were two guys, Dr. Haber and Dr. Bosch, working in Germany to actually make explosives. This is before World War I. So they were ordered to come up with an explosive. So how do you do that? They were taking nitrogen gas from atmosphere, and then they were putting under high temperature and high pressure to make ammonia. So once you make ammonia, as we know, is explosive. There are also historical anecdotes that if they hadn't discovered ammonia, the World War would have ended 2 years earlier. Again, these are other people's perceptions, but again, it also highlights the importance of this process. So the way it's done is in an industrial scale. Now you take atmosphere gas and then you strip other gases, you leave nitrogen, and then you force this to high temperature and pressure so that you can break the nitrogen bond. So when that's broken, then it's combined with hydrogen to make ammonia. Once you have ammonia, then you can make whatever needs to be done, ammonium nitrate, urea, whatever needs to be done from that. That's an easy conversion process. So when we look in the soil, the transformations of nitrogen, we know there's a huge organic nitrogen pool. This comes from organic matter and all the things that happen. And this is in equilibrium with what's called inorganic nitrogen. And you can see from the scale that this is a tiny pool. So when we look at organic, what we have proteins, amino sugars, amino acids. So the process in this case is called mineralization, which means conversion of organic into inorganic forms. And when that happens, then this organic pool is converted to ammonium, nitrate, and nitrite, 3 inorganic nitrogen forms. And again, this is a small pool that's available in the soil. The opposite of this is that other bacteria, other organisms, they can take up these inorganic forms and convert back to the organic nitrogen. And this process is called immobilization. So mineralization and immobilization, back and forth. So in case of mineralization, we are converting organic nitrogen to inorganic nitrogen. And in this case, ammonium, that's the process. And many bacteria and fungi do this process. Okay, immobilization, which is opposite of mineralization, this is conversion of the inorganic forms back to organic nitrogen. Again, organisms do it. We have a lot of microorganisms in the soil in general, and these organisms, they can take up and convert it back into microbial biomass and put back into the organic matter. Okay, another process after organic nitrogen is converted to ammonia, the next process that's extremely important is nitrification. So nitrification means this is a conversion of ammonium to nitrate. And then for this to happen, as you can see, this is oxygen, right? So the first thing that you need is a lot of oxygen. If there's no oxygen, this process is not going to happen. And then you also need pH, and we'll talk about how nitrification can reduce soil pH. And there are 2 sets of organisms who do this conversion. The first set is called Nitrosomonas. This is a set of bacteria. So what they do is there's ammonium, and there needs to be oxygen in the system, and they can change this to another intermediate form called nitrite. And then the other set of bacteria, they act on the nitrite, take more oxygen from the soil, and change it to nitrate. So during this process, there's a lot of hydrogen that's generated. And as we know, if there are more hydrogen ions in the soil, it's going to lower the soil pH. So nitrification generally is considered a process that decreases the pH of the soil, mostly where the fertilizers are applied, or mostly where you have more conversion going on, which is usually the first few centimeters. So talking about soil nitrogen cycle, as we said, pH is critical. Temperature is extremely important. And the moisture and aeration, this will dictate what form of nitrogen will be present at a particular time. So in this case, this example shows the importance of temperature. Here we are at the freezing, and as you see, most of the reactions, mineralization, nitrification, they're not going to happen until you are in mid-70s all the way up to 100. The good thing is this is also the temperature zone that's optimum for growing most plant species. So if there's a good connection, there's a good correlation, you have enough temperature, these processes will happen that will make nitrogen available for plants. So another, moisture and oxygen is extremely critical. So this is an example. This tells you that how much water is in the soil. So here we're looking on the low end, means very dry soil. And here we are looking at a saturated soil. And this tells you the microbial, how many microbes will be there relatively. So in the first example, when we have low water filled, which means relatively moist and dry conditions, in this case, the first process, which is nitrification, which requires oxygen to happen, that will occur under these conditions. When we have a little bit more moisture, as you can see, the nitrification will start declining because there is not enough oxygen in the system, and this is also called aeration limiting step. Now the third step is when we get into waterlogged situation. That's where the denitrification is going to happen, which is opposite of nitrification, which means getting rid of oxygen. And when these things happen, you may wonder, why do microbes do this, right? So the microbes, it's also, they want to survive. They need oxygen to breathe. So and under these conditions, they can't find any oxygen in the soil, so they are going to attack the nitrate molecules. So they can strip whatever oxygen they can get, and when they do that, the nitrate is transformed into nitrogen gas, which goes back into the atmosphere. Okay, so when we add organic materials, there's one indices that you can use to measure what's going to happen to that nitrogen, which is what's called C carbon to nitrogen ratio, which means the relative amount of carbon to nitrogen. So in those materials that have very high CN, which means more carbon per unit of nitrogen, the nitrogen in this case is going to be immobilized, which means bacteria will take that nitrogen, so the inorganic nitrogen pool will decrease. When there is another material with low CN ratio, which means less carbon per unit of nitrogen, there will be more nitrogen mineralization in that scenario. And here are some examples of some of those materials. A good one to look at is sawdust, and look at how much carbon it has relative to nitrogen. So when this is decomposed, it's going to take up a lot of nitrogen that's in the soil. And compare that with biosolids or sewage sludge, and also the broiler litter, and all manures usually have less CN ratio compared with some other materials that have more carbon per unit of nitrogen. So this is another slide when organic materials with high CN ratio are added. So in the first, this is CN ratio, for example, and we know that 20 is about the limit. So if the organic material has more than 20 or 25, you can expect there will be more nitrogen immobilized or not available. So in this example, in the first example, the CN, we're starting with 60, very high, so there will be, that nitrogen will be immobilized, and when that happens, you can see the nitrate level will decrease. And as it progresses more, when the CN ratio decreases, then you can expect net mineralization, which means more nitrate is now reproduced, and that could be available for plants to take up. So when we talk about this, this is critical, that managing CN ratio is critical in terms of figuring out what will be available or what will not be available. So some ideas here that incorporating cover crops when they're in vegetative state is a good idea, and leave mature crops on the surface of the soil so they could be decomposed. And also looking at the plant growth and soil nitrogen is extremely critical, especially when using materials that have a very high CN ratio. So in terms of what plants need, and we know that plants can only use very few forms of nitrogen. So in this example, ammonia plants can take up, nitrate again plants can take up. And then there is a new research that's showing that some small organic molecules, which is present in another what's called dissolved organic pool, some plants can also take up. But this is a relatively small proportion. We don't really know a whole lot about this pool that we need to know. So again, when we're talking about this, we need to keep this nitrogen in the plant root zone, but it's not always possible. So some things that are going to happen is losses. This is an example of volatilization. If it's hot and dry weather, this will happen, and we'll talk about that in a minute. We can also have erosion and runoff of materials that can take nitrogen with it. Again, denitrification can also happen, another loss. It's also leaching can happen in many scenarios that will also result in net loss from the soil. And then again, when the crop uptake that nitrogen, the crop is gone from the field. So soil is depleted with nitrogen. So you could also consider that as a net loss from soil's perspective. So again, talking about the losses, the first is leaching. So what leaches from the soil? So we have ammonia, nitrate, and then we have organics. We'll focus mostly on nitrate, since this is the most mobile form of nitrogen in the soil setting. It happens in the soil profile. And the reason why it happens is, if you look at nitrate, it has negative charge, right? So all the soil particles in the soil are also negatively charged, mostly. So negative repel each other. And nitrate cannot be absorbed in the soil, as you will see in the next few slides, as phosphorus is. So nitrate is mobile, and it keeps moving wherever the water is taking it. It can end in groundwater, surface water, and again, this is a huge economic loss because the goal is really to keep nitrate in the plant root zone so plants can take out. Another example that rooting depth can also influence the nitrogen loss. And here is an example let's look at the peas. So their roots are less than 50 centimeter. And as this nitrate is moving, if it ends up below this 40 centimeter, plant roots are not going to be able to use it. And compare that with wheat, for example, who has a very deep root system. So if this nitrogen is somewhere here, these roots can still capture it before it continues its journey towards groundwater. Another here example is the soil. Soil texture is extremely critical. And we know that in the sand type of scenarios, the water can keep moving. And as the water can keep moving, so can nutrients such as nitrate. In clay soils, the water doesn't move to that depth. So in that scenario, you have more surface runoff issue than the leaching issue. So again, this is minimal under natural vegetation because there's not a whole lot of nitrate to begin with first. And in the row cropping systems, this is higher because we use fertilizers and other things. There's a lot of transformation that happen. Again, the nitrogen management is a key in this scenario. So again, we talked about inefficient, and some of those scenarios could be heavy one-time application. We could also have improper timing before rainfall, for example. Over-application of manure and organics can also lead to more losses, and especially when there are periods of heavy rainfall. That's when you have a greater risk. So what can we do? I think the key is keeping nitrogen in the soils when plants need it. And this is one example. If all the nitrogen is applied at pre-plant, which means there's a big pool that's available to be lost. And in the beginning, plants have less nitrogen requirement, so a large fraction of this pool could eventually be lost. And comparing that with the bottom figure, which is a split application in this case, so some nitrogen is applied in the pre-plant and then some side dress. So this pool is a lot lower compared with this. So you can expect less losses in this example. And that's really the key. Talking about ammonia volatilization, this is again a gas loss to the environment. And this happens when there's ammonia fertilizer applied or urea, which is converted to ammonium. And then in the soil, we have what's called hydroxyl ions. And they can lead to formation of ammonia gas, which goes back into the environment. Again, a net loss from the soil. And this affects all the surface applied nitrogen sources, fertilizer or manures, in this case urea and ammonium. And if there is a warm or dry conditions, it can really accelerate this loss. Here is one example. This tells you on the y-axis is ammonia loss. This is day after application. So as you see that when it's surface applied, you have a higher risk of losses. You also see this variability, what's called diurnal variation. So during the daytime, noon, for example, more hot and dry, you could have more losses as compared with the night. And again, if it's a disc manure or whatever is disc, you can minimize those losses to a great extent. So again, this is where it's key that you need to know where and when occur. First day of application, for example, sunny, warm, low humidity, a lot of wind that can accelerate this loss. And incorporation is a key, and I think this is required in Maryland. I don't know, but you can tell me. So again, the idea here is that spread and incorporate manures early morning or evening when the conditions are not so hot or breezy. That can also minimize these losses. Again, talking about denitrification, I'm sure you guys heard this word a few times. So in this case, the nitrate, again, bacteria are attacking nitrate because they need oxygen. And during the process, they take some nitrogen away. And then finally, they take all the oxygen away, and you're left with nitrogen gas or dinitrogen gas, which goes back into the atmosphere. Again, this is a biological process. Organisms do it. Again, this is a gas form on this side. And it happens, the key for denitrification is there needs to be, the soil must be saturated with water. You can also have some pockets in the soil where this is more prominent than other cases. If it's not water, it's not going to happen because the bacteria are very opportunistic organisms. If they have an oxygen easily available from the soil, they're not going to attack nitrate. They won't do it. And here is a visual, which I think is a great slide, Trish, by the way. And it shows you denitrification in the middle of the field. As you can see, that this is also a little depression, so more water logging conditions compared on the other side, and you can have nitrogen that could eventually escape. And this has a huge influence on in terms of productivity. Now, when you look at denitrification, we want to control. But when you look into other aquatic systems, like water systems, we want denitrification to happen because we want to get rid of nitrogen that's in the water body. So again, in the last few years, we actually have been working on increasing denitrification. So when we talk about crop production systems, we don't want this to happen. We want this nitrate to stay in the soil so plants can use it. Some keys with nitrogen management, again, pH is extremely critical. Runoff erosion losses, again, applying the nutrients when plants need it, again, timely incorporation, and again, cover crops are a great way to store the residual nitrogen in the soil so that a subsequent crop can utilize it. All right. So again, now switching gears and talking about phosphorus. And again, phosphorus is a simpler cycle, and it has different issues than nitrogen. It has no gas form, which could be good or bad thing, because with the nitrogen, we can convert it into gas form, and our fields won't have nitrogen problem. But with phosphorus, it's not going anywhere. It's going to stay in the soils. Again, we have phosphorus that's soluble. It can be fixed and slowly go to other forms. And this kind of shows you all the forms that are available in nature. Doesn't mean in the soils. So in the soils, the most critical form is orthophosphate. Although we do have other pools such as organics and some other forms that are available. Elemental phosphorus, you're never going to find in the soils. Again, so looking at phosphorus cycle, let's look at inputs first. So we have fertilizers, residues, we have waste, and we have all other organic products. When we look at the losses, in this case, we are looking at erosion, surface runoff, for example. And then we also have a huge organic phosphorus pool in the soils. This is organic matter, soluble organics, and also the microorganisms that are in the soil. A lot of phosphorus in the soil is fixed in different processes, and we'll talk about them in a little bit detail. One key thing here to notice is that in the middle of this is the soil solution pool. This is the only pool that plants can utilize to grow. But also notice that everything is in equilibrium with this pool. And what that means is, as plants will take up the soil solution pool, there will be phosphorus that will be released from here, and it will replenish the soil solution pool. As this pool gets depleted, there could be some phosphorus that can contribute through this route. So it's critical to look at the total soil phosphorus pool compared to just a soil solution pool, and that's part of the problem. When soils get saturated with phosphorus, there's no way around, because the phosphorus is going to go through these pools as you have more phosphorus, and then eventually, as we start depleting, more phosphorus is going to come to soil solution. We talk about transformation similar to nitrogen. Again, the organic phosphorus pool is huge, and again, there are two processes here, organic to inorganic. These are, by the way, phosphorus species that are present in the soil solution. They're just called orthophosphates for simplification. Again, this is mineralization, organic to inorganic, and immobilization is conversion back to organics. So when we talk about plant available pool, this is the orthophosphate or water soluble pool, and there we have these two species that are most abundant in the soil. What you see on this slide is that depending on the pH, you can have a particular species present in higher amount. So, for example, here you have more H3PO4, and as the pH comes to close, this is almost gone. And then you have a second species that takes over close to 5 pH, and then as the pH goes up to the higher, more than 11, then this disappears and other species shows up. But another way to visualize here is this is phosphorus availability, and on this side you have acidic soils, and this is alkaline soils. So when the soils are more acidic, there's going to be more iron and aluminum who can fix phosphorus. At higher pH, it's going to be calcium. So where you're going to find most phosphorus available is this narrow range from 5.5 to 6.9. That's where you're going to see most of the phosphorus available. And phosphorus is also different. It moves by diffusion. And what that means is that it's not going to go to plant roots because the plant roots is there. It's going to go either with water that's going to touch the roots, or it's going to go from an area where there's more phosphorus to less phosphorus. So that's why the phosphorus management is a little bit different than other nutrients. This is another process we call fixation, and in this process, the phosphorus is fixed via two processes. One is called adsorption, or another word for that is sorption, which means it's fixed on iron and aluminum oxides, just on the surfaces. And another word is called precipitation. So again, the difference in these two is that it's gone from the soil solution. This is more strongly fixed when it's precipitation than adsorption. Talking about adsorption or sorption, so in the acid soils, as we talked about, it's mostly iron and aluminum. In neutral alkaline soils, it's more calcium that fixes this phosphorus. Another here is the secondary minerals. Again, in this case, in acid soils, phosphorus is again combining with iron and aluminum, but actually forming minerals now compared to just sticking on the surface. And in case of calcareous soils, it's going to form insoluble compounds. And one example of that mineral is apatite here. So again, this is another slide to visualize the phosphorus availability. This is soil pH. This is how much would be available. And as you see, this is the relative available phosphorus pool. And you're going to see most of that available from about 5.5 to less than 6.8. So managing pH is a key to making sure that there is enough phosphorus that is available in the soils. Again, it's when the phosphorus is fixed, which is the first pool, it's more available because it can go back into the soil solution. And as time goes on, there's a more iron and aluminum that keep combining with phosphorus. And that's what forms phosphorus minerals. Another word, which actually not very often used these days, is called polluted P. It just means that the phosphorus is so strongly fixed that it's not going to be easily available, or in this case, the term is used unavailable, not available anymore. This is another way to sort of look at the whole phosphorus cycle. So this is the soil solution. This side all are your inorganic forms. This is your slowly exchangeable, which is the mineral phase. This is the sorption, adsorption processes. And this is all the organic phosphorus pool. Again, these are microbes that die, mineralizes, phosphorus comes into solution. Microbes take up phosphorus, immobilization, and then they die, and then they contribute to organic matter pool. So everything is in equilibrium. It's so when you're working or looking at phosphorus, it just shouldn't be looked in an isolation. Having a good understanding of phosphorus cycle is critical, so we can manage this in a way that it doesn't leak from the system. So again, talking about phosphorus loss pathways are relatively easy because there's no gas form. So the way it can happen is erosion and runoff happens more on the slopes, and then you have leaching that could happen through the tile drains, ditches, and also through the soil profile. Again, then crop uptake that could also be construed as a phosphorus loss pathway. So again, pH is more critical in this case, even more critical than nitrogen. Phosphorus fertilizer, they need to be, when they are needed, again, the starter fertilizer, because phosphorus moves by diffusion. So the roots are not going to go to phosphorus. Phosphorus has to somehow get closer to the roots so they can grow. again, we need to reduce losses somehow by erosion and runoff, because once this phosphorus gets into water bodies, it's impossible to remove it. So here is another question. The question is, what is the optimum pH range to maximize the plant availability? And you have 4 options. Okay, awesome. So the answer is B. So very good. I think you guys are going to do awesome. Okay, so coming to potassium, which again is an easy nutrient in terms of managing. So it's again a simpler cycle. We don't have many reactions that happen with nitrogen. So a couple things can happen to soluble potassium. It can be fixed or less available. It has different mechanisms. There are minimal water quality issues. We never talk about potassium with water quality because it's not a concern. This is a great way to sort of visualize the potash cycle. So looking at sources again, you probably see a common theme with all nutrients that you have: fertilizers, plant residues, manures, organic matter. And then also in this case, there's another pool that's called exchangeable potassium pool in the soil. And in the middle, you have a big soil solution pool. Now, when we talk about losses, erosion, for example, is also a concern because potassium stays in the soil, and if the soil is moving, so will potassium. There could also be issues with potassium leaching. And then there's another pool which is also considered losses, is what's called structural potassium. So in this case, potassium gets into the rocks and minerals, and then it never comes back. So when we talk about plant potassium, this is potassium. It's again dissolved in soil solution that's going to be available to plants. There will be also exchangeable, which we'll talk in a minute, that's also available. It also moves by diffusion, just like phosphorus. Wherever water is, it can slowly move. When we talk about soil solution, when you look at the total potassium in the soils, it's a tiny pool, but it's enough to provide what plants needed. It's rarely available for plants to take up. Another pool that's available to plants is called exchangeable potassium. So this is the exchangeable pool, which means exchangeable means that potassium can be exchanged back into the soil solution, so plants can take it up. It's also rarely available. It's about 1% of the total potassium. So in the first, it's going to be the soil solution where plants are going to take this potassium. As this is depleted, the exchangeable potassium will exchange potassium into the soil solution so plants can take it up. Now, this is another pool that's also considered loss, is the fixed potassium. So in this case, the potassium is trapped between the mineral layers. And once it's trapped, it can't be exchanged. Weathering of minerals can contribute, but not a whole lot. And this is again about less than 10% of the total potassium in the soil. And this is how this fixation happens. So this is potassium and other ions. These are 2 mineral layers. So they get between the 2 mineral layers, and then it's not released back into the system. So it's gone by that time it gets into that phase. Now another one here is structural, which happens in this case. This is the structural potassium. This is where most of the potassium in the soil is stored. And in this case, it becomes part of the mineral. And the 2 examples here are mica and feldspar, which are 2 rich potassium minerals. And that's where most of the potassium is. They say relatively unavailable. What that means is under normal circumstances, it's not going to be, unless all the potassium from the soil solution, exchangeable, is depleted, then eventually it can be released back. But on the time scales we are looking at, it's going to be unavailable. So loss pathways: leaching, coarse textured soils, sandy soils, high rainfall, erosion. And one unique thing about potassium is that plants do like to spoil themselves. So if there's more potassium, they're going to take up more. So this is also another loss pathway, because if plants take more than what they need, it's gone from the soil. So for next crop, we need to make sure there's enough potassium that's available. And the word that's used is called luxury consumption. And this is an example. This is potassium content of the plants. This is what plants typically need. But if there's a more potassium in the soil, then plants are gonna say, oh, we'll take a little bit more. And when we harvest the plant, it's gone. So again, a net loss. And it could be a loss if especially that potassium is applied through fertilizers. So when we're talking about potassium management, with most of these nutrients, the pH is a sort of key. When you get into the low extremes or higher extremes, it's not conducive for plants to grow to begin with. And then you could have another deficiency symptoms that are triggered because of changes in pH. So a lot of problems can be avoided just having the right pH. And again, erosion is a key because that's where most of the potassium could be lost along with other nutrients. And in this case, it's talking about how to reduce luxury consumption. Again, if there's more potassium available, plant's going to take up more. But if you supply a little bit, then you can minimize that loss. So I think we have an easy question which talks about how is potassium lost from the soil. And one is microbial transformation to gaseous. Another is leaching, and then the third is the luxury consumption. There you go. Yes, so C will be the right answer in this case. All right, so just to kind of summarize, when we talk about nutrients, the first thing that's going to come into soil solution. So everything has to be in the soil solution for plants to take up. And this is also in equilibrium with another pool, what's called the labile pool. For nitrogen, it's going to be the mineralizable organic matter. For phosphorus, it's going to be the sorption or desorption process. For potassium, it's going to be exchangeable pool. So they all are in equilibrium. And then we have what's called the stable pool. For phosphorus and potassium, it's going to be the soil minerals. For nitrogen, it's going to be humus. And probably you notice that there's no nitrogen mineral in the soil, right? So because most of the nitrogen in the soil is in the soil organic matter. So that's where it stays. And the plants and microorganisms can only use the soil solution pool. But everything is sort of connected. It comes back to this pool. So if you have more questions, feel free to send me an email. I am active now on 2 emails, so it's kind of fun to see who do I respond first. But I mean, if you have any questions, send me an email, and my goal is to get back to you within 48 hours.